Welcome everyone. Today we're going to be looking at L'Hopital's rule and indeterminate forms as well. So on the notes here, up at the top, just a few kind of introductory examples to remind us of how we worked with limits in the past. So we've got on the left-hand side here an infinite limit and then two limits approaching specific numeric values. So if we were solving each one of these, you can take a moment and solve them yourself. Go ahead and pause the video if you want. So if we look at the first one, clearly we're looking at an infinite limit that's approaching infinity, and we can look at the exponents, so we can see that this limit is going to equal -7 by inspection. Clearly, if we wanted to be a little bit fancier, we could multiply the numerator and denominator by the highest degree, multiply by the reciprocal of the highest degree, and we would get the limit as x goes to infinity of -7 over 1 plus 2 over x squared, which as x goes to infinity, 2 over x squared will go to 0, and we'll end up with -7 over 1. So this would be kind of the more formal way of writing the work, obviously. But -7 is obviously the limit here. If we move to the second example, this one's going to be a little bit trickier because we're approaching x equals -3. So we could have a vertical asymptote, we could have a hole, or we could have a limit. So the easiest quick check would be just to directly substitute in -3. So by doing that, we'll get -27. Positive 27 minus 27 over -3 plus 3, which gives us 0 over 0. So the 0 over 0 term is what we call an indeterminate form. It's not going to fit. Let's try that again. Shorthanded. Okay, so that's our indeterminate form, 0 over 0. The other type of indeterminate form you can have is infinity over infinity. These will be the two most common. There are other indeterminate forms, which we'll look at a little bit later, but these are going to be the two most common. So we've got indeterminate forms. So suppose we don't know L'Hopital's rule, though, and we wanted to evaluate this. The way that we did it in the past would be to do a little bit of algebra. So we'll take the limit as x approaches -3, and we can factor out a 3 in the numerator, and that'll give us x squared minus 9 all over x plus 3, which then we can factor the difference of squares. And clearly cancel out that denominator value with the numerator factor. So we'll be left with, when we evaluate at -3, 3 times -3 minus 3, which is -18. So the limit's going to equal -18. Clearly, it's going to have a hole in the graph at -3. So those values are going to represent a hole in the graph, but the limit will still exist. Okay, so then moving on, third example is really same example, only we're adding in an exponential function instead of just a typical polynomial. So we can use the fact that if we do direct substitution, we'll still get 0 divided by 0. So it's still going to be indeterminate, so we'd have to use another method. So we're going to use factoring again. So we've got, note, e to the 2x is the same as e to the x squared. So the numerator is really just the difference of squares. And we'll we'll get some nice cancellation in the denominator again with that numerator factor. So we're left with the limit as x goes to 0 of e to the x plus 1, which is just going to be e to the 0 plus 1, which equals 2. So what L'Hopital's rule is going to do for us is it's actually going to allow us to evaluate limits that follow these kind of forms, but it's a quicker method in a lot of cases. Now, in some cases, we have to use it because we won't have a factoring method to use necessarily. But it's really just here for the usefulness of it. So down below here is kind of the standard definitions that you'll see for it. So I'll let you read through that. The key that we're going to be looking for is the indeterminate form. So we have to verify that we have an indeterminate form of some kind. And there's going to be other ones, of course, but these are going to be the most typical ones that you'll see in introductory uses of L'Hopital's rule. And what L'Hopital's rule says is that if we have an indeterminate form, so 0 over 0 or infinity over infinity, plus or minus, then the limit of the ratio of those two expressions, so our limit's going to look like a ratio of two functions, could be polynomials, trig functions, exponential functions, log functions, any type of function that we worked with. Then what's also going to be true is that the limit of the ratio of the derivatives of each one of those separate functions, the numerator function and denominator function, is going to give you the same limit. So that's going to be really, really useful because that f prime g prime expression might be much easier to evaluate with a limit than f and g together. So there are some caveats, of course. G of x cannot be 0. And then g prime of x we'll definitely hope is not 0 as well, right? So we're going to assume that that's not 0. Because if we get 0 for either one of those, then we could have an infinite limit, so where L'Hopital does not apply. Okay, so let's go ahead and move on to the first few examples here. So we're not going to complete all of these, but we'll get a head start on these before we start the next video. So looking at number 1, we've got a nice rational expression here. If I plug in 1 to the limit, I get 0 divided by 0. Therefore, L'Hopital will apply. So we can just say by L apostrophe H if you wanted to, or by, you could spell it out all the way if you want. L'Hopital's, oops. We can say sometimes it's just by L'Hopital, the limit as x goes to 1 of that original limit expression is going to be the derivative. So the derivative of the numerator is 9. X to the 8, the minus 1 becomes 0. And on the bottom it'll be 5, x to the 4th. So substituting in 1, we get 9/5. So the limit will be 9/5. You can verify that graphically as well at 1. But we get 9/5. So again, much easier than trying to figure out how to factor this. Clearly factoring this would be tricky because x to the 5th minus 1 isn't a nice difference of cubes or difference of squares. Okay, so looking at number 2, now we've got some trig functions. So again, we'll do a quick check here. So if we plug in 0, sine of 0 is 0, tangent of 0 is 0. So we know L'Hopital is going to work here. So the derivative of sine 4x is going to be 4 cosine 4x. And the derivative of tangent 5x is going to be 5 secant squared 5x. And at 0, cosine and secant are both going to be equal to 1. So our answer is 4/5. Now for the AP, the key idea here is that you are explicitly recognizing that L'Hopital is what you're applying. So don't just go simply into the work. Give me some quick statement of by L'Hopital's rule. You can shorthand it a little bit, but clearly you want to show that you're using L'Hopital's rule explicitly. Okay, so we'll do a couple more here, and then we'll stop the video and we'll move part 2 for the remaining examples. So for number 3, we can plug in pi, it looks like. So we're taking the limit as theta approaches pi from the left. So this is going to be a one-sided limit. So if we plug in pi, sine of pi is 0, and cosine of pi is -1. So what we get here is 0/2, which means the limit is equal to 0. So if you're working on a problem where you think L'Hopital might apply, do not use L'Hopital until you've tested the limit at the value that you're describing. So in this case, this is a trick example where some of you might jump in and just immediately differentiate the expression, and then you're going to get a problematic value because L'Hopital does not apply here. So L'Hopital is not needed for this limit. Okay. So just keep that in mind and be careful when you're working on problems where you think you might be using L'Hopital. Okay, so that's the first 3 examples there. We've got a few more. So I'm going to stop the video